Section 7.1 Sequence and Series. A sequence is a function that computes an ordered list. For example, the average person in the United States uses 100 gallons of water each day. The function f of n equal to 100n generates the terms of the sequence. So when we plug in n equal to 1, we're going to get the first term, 100. N equal to 2, that will be 200. N equal to 3, that will be 300. So we do have an ordered list in here, and we call this is going to be the sequence. N equal to 1, n equal to 2, n equal to 3. The function will present the number of gallons of water used by the average person after n days. So after 3 days, the person in the United States used 300 gallons of water on average. A second example of a sequence involves investing money. If $100 is deposited into a saving account, paying 3% interest compound annually, then the function g of n equal to 100 times 1.03 to the power of n calculates the account balance after n years. The terms of the sequence are, so you're going to plug in n equal to 1, n equal to 2 into this function. N will represent the year. So the first year, you could plug it here, that will be 100 times 1.03. So you're going to get 103, the first year. That will be including the interest. N equal to 2, the second year. He's gonna get $106.09. Okay, so this is gonna be the sequence. An infinite sequence is a function having for its domain the set of natural number 1, 2, 3, 4, 5. Remember, natural number is starting from 1 or the positive integer. And we call this as infinite sequence. Means it's going to be dot, dot, dot. It's going to be going forever. And then we have another one called finite sequence. Finite sequence is a function having for its domains a set of natural numbers. 1, 2, 3, 4, 5 until n. Okay, they're going to stop at the n terms here. So this is called the finite sequence. As another example, consider the sequence given by, I do have a of n equal to 3 to the power of n. Or sometimes we could write a n equal to 3 to the power of n. The notation a n means the same as a of n, but is used more commonly with sequence. Some function values call terms of the sequence followed. So when I plug in n equal to 1, we're going to plug in this formula. So you do have a 3 here. So a1 equal to 3. a2, we plug it in, you're going to get the 9. So a3, that will be equal to 27. a4, that will be equal to 81. Okay, and then the first term of the sequence is going to be the a1. So this is the first term, second term, third, and fourth. The fifth term will gonna be a5, okay? And then we do have an nth term, okay? Just like this guy, nth term. And also, we could call this as the general term, okay? Sometimes I will ask you guys, I'm looking for the general term an. And you can see this is gonna be the infinite sequence because you're gonna see dot, 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 you're gonna be keep going forever. Okay, if without these 3 dots, that would be the finite sequence. Okay, example 1, finding terms of the sequence. Write the first 5 terms for each sequence. So you're gonna plug it in, n equal to 1. So you do have a 5 times 1 minus 2, which is gonna be equal to 3. a2, plug it in, 5 times 2, which is going to be the 10, minus 2, that will be the 8. So a2 equal to 8. I want you guys try to plug it in, find out the first 5 terms. So check your work. Okay, B. You could see that's a negative 1 to the power of n plus 1. Okay, you're gonna see some of them is gonna be positive, some of them is gonna be negative. For example, when n equal to 1, I have a 1 plus 1. So negative 1 squared. So the negative is gonna be goes away. And then times 1 squared, so which is gonna be positive 1. And then A2, so plug in n equal to 2. So this is gonna be the odd number. Then that will be negative 1. So negative 4. Okay, 2 squared, which is gonna be 4. Plug it in. Check your work. So 1 positive, 1 negative, 1 positive, and 1 negative. Okay, this one. Find out the first 5 terms. Okay, check your work. Converge and diverge. If the terms of an infinite sequence get closer and closer to some real number, the sequence is said to be convergent and to converge to that real number. For example, the sequence divided by an equal to 1 over n approach to 0 as n becomes larger. So you could plug it in when n equal to 1, you're going to get the 1. N equal to 2, that will be going to be 1 half. When n equal to 2, that will be 1 half. N equal to 3, that will be 1/3. So you're going to see the number is going to be getting approaching to the 0. Okay, the graph is going to be looks like that. The first one, when n equal to 1, I got n equal to 1 and then an equal to 1. Second terms, n equal to 2, an is going to be 1 half, which is going to be 0.5. Okay, so you keep plugging the n here. As n becomes larger, you're going to see this line is going to be approaching to 0. Okay, it's approaching to 0. And we say this is going to be the convergent. And the sequence converge to 0. This number is going to be approaching to 0. So that converge to the 0. So the terms of an is approaching to 0. So you know this sequence is convergent. And the sequence converge to 0. A sequence that does not converge to any number is divergent. The terms of the sequence an equal to n squared are the divergent. Okay, so you can see this number is getting bigger and bigger as n becomes larger. So this sequence is going to be diverge. And the value of the an do not approach a fixed number. Rather, they increase without bound. Okay, so this is going to be the diverge sequence. Recursive definitions. Some sequences are defined by a recursive definition, one in which each term after the first term or first few terms is defined as an expression involving the previous term or terms. On the other hand, the sequence in example 1 were defined explicitly with a formula of an that does not depend on a previous term. Let's look at this example. Using a recursion formula, write the first 4 terms for each sequence. So you can see I do have the first term, a1 equal to 2, and then I have an equal to 3 times an minus 1. So you always need to use the previous term to find the new term. And we call this is recursive formula. So let's try to plug it in, write down the first 4 terms. They already given a1 equal to 2. So you're going to plug in n equal to 2. 2, that would be equal to 2 minus 1 here. Okay, So you know 3 times A1, which is going to be your 2. So multiply it, 6 minus 1, you're going to get the 5. Okay, and then the A3, you're going to use the A2 again. Okay, plug into this general term and find it out, the first 4 terms. Okay, check your word. You should get this. So the sequence is going to be 2, 5, 14, and 41. Okay, try the example B. This time A1 is going to be equal to 5. And this is the general form. Okay, so first plug in n equal to 2 here. You're going to get A2 equal to A1 plus 2 times 2. Okay, so A1 equal to 5. 5 plus 4, which is going to be equal to 9. Okay, check your word. Okay, second part, series. Given the infinite sequence, so this is the infinite sequence, you're gonna see the dot dot dot. When we added up all the terms together, we're gonna get s to the infinity, okay, because it's gonna be going forever here. When I add up all the terms, a1 plus a2 plus a3 until an, we call this as infinite series, and it's denoted by s infinity. Okay, series means you want to add up all the sequence, that will be the series. And if this is an infinite sequence, when you add it up, that's called infinite series. If we do have the partial sum, okay, you could think about this as a finite sequence. Okay, they're gonna stop at the general term here. When you add it up, we call this as the partial sum. And sum of the first n terms. So we do have Sn equal to A1 plus A2 until An. And we call this is going to be finite series. And it's denoted by Sn here. Okay, one more time. Series means you're going to add up all the sequence. That will become series. So we do have an infinite series and the finite series. Okay, series and summation notation. For example, the infinite sequence. So we do using the comma. So this is called the sequence. And then we have a dot 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 at the end. So this is the infinite sequence. Defines the terms of the infinite series. How can you make it like infinite series? You just need to add it all up. Okay, so this is a s infinity equal to, add up all this guy together. Sigma notation. When the general term of the sequence is known, the Greek letter, this is called the sigma, okay? Sigma can be used to write a series, and this is means like you want to add it all up. For example, the sum of the first 3 terms of the sequence is 5, 8, 11. And then the general term will be 3k plus 2. Can be named as the phono using the sigma notation or summation notation. Okay, summation notation means you want to add it all up. So you could try, plug it in. When k equal to 1, so you do have a 3 times 1 plus 2, which is going to be 5. And then k equal to 2. Okay, so plug it in. 3 times 2, you're going to get a 6. 6 plus 2, that will be equal to 8. Okay, so at the end, this number will represent the n terms. K equal to 3. So we're gonna stop at here. Okay, one more time. This is a sigma notation, summation notation. This is means you want to calculate the starting term, k equal to 1, and then k equal to 2, and then k equal to 3. You want to stop at the 3 here because the ending term, That's 3 here. And then you want to add it all up together. Okay, series. A finite series is an expression of the form. We do have a Sn equal to A1 plus A2 plus A3 until An. Okay, the last term is n. So that's why the ending number here, that will be the n here. And then we want to start with 1. The first term is going to be 1. So I equal to 1. And this is called the finite series because we stop at the end here. How about the infinite series? Infinite series, we're gonna put the infinity here. Okay, starting from I equal to 1, I equal to 2, until I equal to n, the general term, and then keep going. So you're gonna see that it's the infinity here. And we call this is infinite series. Okay, example 3. Using summation notation. I want you guys try to calculate this guy. This is talking about the first term, j equal to 1. And then j equal to 2, j equal to 3, j equal to 4. At the end, that will be j equal to 5. Okay, and then I want you guys add it up together. Try. Okay, check your work. This is j equal to 1, j equal to 2, j equal to 3, j equal to 4, and j equal to 5. Okay, and then we're gonna add it all up. You're gonna get 75. Okay, example 4. Write the terms for each series. Evaluate each sum if possible. Okay, so here plug in I equal to 1 until I equal to 5. So just plug it in, that's it. B, same idea, j equal to 1 until j equal to 4. And then they given what is your x1 equal to. So for example, when j equal to 1, you're gonna have a 2x1 minus 5. And then x1 will be equal to 3. So 2 times 3, which is gonna be 6, minus 5, which is going to be equal to 1. Okay, plug it in one by one. Okay, plug in the numbers. So you should get 28 here. Okay, one more example. You will have the delta x here, and the delta x that will be equal to 4. Okay, and then f of xk. So when k equal to 1, you're gonna find out x1 is gonna be equal to 1. So you're gonna plug in this formula. Okay, I will just try to work it out first and then do it like one by one. Okay, so you should get 92 over 15. Summation properties. If A1, A2, A3 until AN and B1, B2 until Bn are two sequences and C is a constant, then for every positive integer n, the following hold. Okay, so when your C here is a constant, so it's any real number. Like for example, there's a 2 here. So you could just write it out, it's going to be n times C. Or this guy, AI, is going to be the general term, and C is a constant. Since this is a constant, you could take it out. Okay, make sure you're going to add the parenthesis. Okay, C, parenthesis, and then A1 plus A2 until AN. And then you have the two general terms, AI plus BI. You could break it down. Just looks like you distribute it, the summation notation here. Same idea for the subtraction. Okay, and then summation rules. If I have the general term just I want to add it up from 1, 2 until the n terms here. So this is going to be the formula. You're going to use n times n plus 1 over 2. So you could calculate this guy, what is going to be equal to. Second one, when you have I square here, 1 square plus 2 square until n square, you could use this formula. N times n plus 1 times 2n plus 1 over 6. Last one here, when you have I to the power of 3, and that will be the formula. This is how you guys plug in the number and then calculate the partial sums here. Example 5, using summation properties. Use the summation properties to find each sum. So this one, we do have only like the constant. So you could use this properties, right? That's a C here. So you're going to do n times C. Okay. N times, the n is 50 times the C. This one, you do have a 3 here. The constant, you could take it outside, right? And then this is only like I. So I, that will be here using this formula, n times n plus 1 over 2. Okay, so plug in this formula, n times n plus 1 over 2. C. We do have 2 guys in here. So we kind of like distribute the summation notation, right? And this one, the constant 3 is going to be put it outside. And then we have the formula for the I square here. And this one, that will be C times your n, right? So 5 times 10 here. And then this I squared, that will be the formula. So you should get 1,205. Okay, number 6. One more time, you could distribute the summation notation for each terms. And this guy, we could use the formula. The 2, you could take it out. We do have a formula for the I also. And this is going to be n times C. So 8 times 5 here. So you should get 215. That's it.